In exercise number 40, we are asked to find the volume of the solid bounded by the cylinders x squared plus y squared equals r squared, and y squared plus z squared equals r squared. So if we think very roughly, and this is going to be an extremely crude drawing, even without having to wrestle with a tablet when I'm just working on a chalkboard, I usually have a great deal of difficulty figuring out how to draw this thing. So let's just kind of do a crude estimate here. X squared plus y squared equals r squared. So r specifies some constant radius. This describes a circle in the xy plane. Let's assume the usual orientation of things. So we have some circle in the xy plane, and since z is unbounded, that means that gives us a cylinder, a vertical cylinder. Terrible sketches. Okay. The other one is y squared plus z squared equals r squared. This is a circle of radius r, and now that's in the yz plane. So you're going to have, let's see, that's intersecting there. So that'll kind of come up and back down that way. And that is going to be a cylinder that comes out in the x direction, right? I'm barely even trying on this back part. That's going to take forever. So we have these two cylinders here. And together, these are fully closed off. And there's this weird knobby thing in the middle of all of this that I have never been able to successfully freehand sketch, even on a chalkboard or on a piece of paper. You might be able to visualize what it is. Thankfully, we don't need to visualize it perfectly. We can consider a couple of important factors here. One of them is that we can interpret this. What am I doing? Why? There we go. The horizontal cylinder, the cylinder centered on the x-axis, gives us kind of an upper and lower surface. Z can be thought of as a function of y and x on the upper surface and also on the lower surface. And this is all constrained to be within the vertical cylinder, the one centered on the z-axis. Now, the vertical cylinder is the one whose sort of footprint in the xy plane is the circle of radius r. So we can say that we have this region D as a domain of this thing. And if we integrate over this from the lower bound on z to the upper bound on z, between those values, then we would get the volume. And that's really messy to describe. So let's consider instead just the sort of first octant piece. There's a certain amount of symmetry here. Hopefully you can see that in the, if we just consider the part in the first octant, so that'll be the first quadrant in the xy plane, and also the upper part of that rather than the lower. So note, looking down on this, that each of the four quadrants should give you equivalent pieces, just rotated. And then within each quadrant, the part that is above the xy plane is equal to the part that's below the xy plane. So that means that we could describe the total volume V as being 8 times what I'll call V sub 1, the volume in the first octant. So if you can see that symmetry, that'll allow us to simplify this. If you don't see that symmetry or you aren't certain about it, you can just set up things. Instead of lower bounds of 0, I'll have a bunch of lower bounds of 0. Instead, you would go from like negative r to r, for instance, or from a negative square root to a positive square root as we work through this. But if you are in a situation with that kind of symmetry, breaking that down could simplify things a bit, and we'll we'll see that how that helps us out once we get to the stage of evaluation. It's important to keep in mind that this works because we're just evaluating volume, and this object is symmetric. If we're trying to evaluate an integral that has an integrand that is non-constant, then just the region being symmetric is not going to be enough for us to just say, oh, well, let's just do this part and then multiply by a constant. Because the function itself, the integrand, would also have to have the same kind of symmetry that you're using. And if it doesn't, then you'll have a problem because you might have a symmetric region, but your function values would be different in one part than another part. But since we're just finding volume, then this should be fine, and we don't have to really worry about that so much. Now we need to consider the question of how to set this thing up. Well, we see from this thing here, we have this y squared plus z squared equals r squared. So the region, the surface we are integrating under would be z equals, you'd have r squared minus y squared, and you need one of the square roots of those. We're just going to take the first octant, so we'll have the positive square root of r squared minus y squared. So this will be our integrand. This describes the surface. We'll be integrating that function. As far as the bounds here, we see x and y both go between 0 and r. The descriptions of this circle, with one in terms of the other, we can solve this and write y equals the square root of r squared minus x squared. Or we can solve for x and get x equals the square root of r squared minus y squared. Whichever one we do, the other variable is going to go from 0 to r. Right? So we could say, for instance, that v1 is equal to the integral from 0 to r of the integral, and I'm thinking of 0 to r being the x value. Then y would go from 0 up to what we found here, the square root of r squared minus x squared. Our integrand is the square root of r squared minus y squared. And this was dy dx. So that's one way to set all of that up. Alternatively, we could say that v1 is equal to the integral from 0 to r, that's y ranging from 0 to r, and x can run from 0 up to, we found that x would be the square root of r squared minus y squared. Again, our integrand is the z value, square root of r squared minus y squared. And this would then be dx dy. These are two ways of setting this up. Very similar, slightly different in terms of whether, there's a lot of symmetry here. You can see when we write these, there's a whole lot of symmetry. And it's just a matter of which direction we want to choose our order of integration first, because that governs whether we have the x or the y in the numerator. So, looking at how much symmetry there is, you might think that it doesn't make much of a difference which way we evaluate this. But if we take a look at the integrands, we see that those are the same in both cases. We will be integrating this expression first with respect to one of the variables, either y or x. And it's a question of which one we want to do first. If we integrate this first one here with respect to y, looking at the form you have, that doesn't work well with a u substitution or anything. Unless you have that integral memorized, which I don't, it looks like we're looking at some sort of trig substitution, and that does not sound fun, right? So let's try this second form. I'm going to separate that, and we'll evaluate the second one. Now, by the way, from the setup here, you might recall what I stressed in the notes and the previous video, that the outermost integral has to have constant bounds. R is constant in the context of this problem. They were talking about the volume of a solid bounded by these particular cylinders. That only makes sense if the cylinders have constant radius. So R is some fixed radius, and that is a constant throughout here. This next one stepping in here, R is constant. It's only a variable depending on y, and y is the outer integral. So that does still work out fine. So we're okay. Starting to evaluate this, we need to evaluate this inner integral. But notice the square root of r squared minus y squared is constant with respect to x. So we just have the square root of r squared minus y squared times x evaluated from x equals 0 up to x equals the square root of r squared minus y squared. Those are the bounds on that inner integral. And then just copy that part dy. So these bounds in this integral right here are what gave us the bounds on this evaluation right here. So we have the square root of r squared minus y squared times, now what do we have here? Well, plugging this in for x, that is a square root of r squared minus y squared. And then we have minus 0. So that just goes away. You can see why it's nice to have a lower bound of 0 whenever it's possible. That's why the symmetry helps us out so much. So of course now this product simplifies very nicely, doesn't it? That is just r squared minus y squared with no square root, because we're multiplying it by itself. Now we can, you might still be following along a little bit, so maybe I shouldn't scroll quite that far. Let's go to here. Now we can integrate this dy. So we have r squared is constant, so we get r squared y minus 1/3 y cubed, evaluated as y runs from 0 to r. If you feel uncertain about remembering that r is constant and not variable, you could write y equals 0 to y equals r. But in this problem, we've been using r exclusively as a constant, so we don't strictly have to do that. So it looks like we get, plugging in r for y, we get r cubed minus 1/3 r cubed minus, plugging in zeros, we get 0. So we have 2/3 r cubed. Now what was this? Let's follow this chain of equality back. This was equal to this, which was equal to that, blah, blah, blah. Rolling all of this back, we get to v1. That's v1 and not v. V is equal to 8v1. So we have 8 times 2/3 r cubed, which should be 16/3 r cubed. Let me make sure in my notes that I did not make any computational errors along the way. And yes, there we go. 16/3 r cubed is the volume in question. So whatever r is for these particular cylinders has to be the same radius in both, of course, and have the same same value on both of those. But whatever the weird, knobby, funky little solid is that we get bounded by these two cylinders, by taking advantage of some of the symmetries, we're able to compute this. Again, you could do this without that and recognize that, you know, for instance, your z is going to be the difference of the upper minus the lower, and that'll end up just being 2 of those, so you could have a 2 in there. And then your lower bounds here, you'd have a negative r, sorry, down here you'd have a negative r, and you have a negative square root of r squared minus y squared. And that negative square root of r squared minus y squared would end up introducing a factor of 2 here. When you subtract the 1 minus the negative of that, you'll get a 2, so that'll pop out. And then when you have the from negative r to r and you're evaluating there, you'll get some duplication of things. That'll be another factor of 2, and altogether that's where the 8 will come from. You'll have a 2, a 2, and a 2, and that'll pile up to make the 8, and you'll get the same result at the end. You could try that if you wish.